So hi everyone, and thank you for the introduction. So we'll talk about how VR impact guest behavior in collision avoidance. And I will start with showing you a small video of a person walking in the street. This person was wearing glasses with a camera to record what he saw, but also equipped with a gaze tracker to record what he looked at. And just next to this video, another video of the same situation, but in virtual environment. And in our work, we are wondering if gaze behavior is similar in a real and virtual environment. So first, why you want to study gaze behavior in this kind of situation? If we took this little example, where a person wants to reach a goal, and he had to avoid the other worker in order to reach it. If we look at just only on the trajectory, we'll see that he performed some maneuvers to avoid these three walkers. And now, if we add the gaze, what you can see is that first you look at the first walker, then you will look at the other two walkers and go between them. So using gaze behavior, we can say that the gaze behavior will help us to understand why he did this maneuver, which other worker he chose to avoid and to do this maneuver. So there's been some work on gaze and locomotion. Merhoff shows that gaze attract worker with high risk of collision. Jovancevic shows that depending on the interaction, the gaze behavior will be different. And Croft look at the gaze behavior and crossing order. Kitazawa look at proximity and gaze behavior. So all these experiments were done in either a real or a virtual environment. And now, why for us we are interested in gaze behavior in virtual reality? It's because virtual reality offers a better control of the experiment. As for a situation with other workers, there are complex situations, lots of interaction, and it's nearly impossible to add the same experiment for all participants when there's lots of workers. However, in a virtual environment, we control the trajectory, the movement of all the workers, so we are able to replicate the same situation for all the participants. And it's why virtual reality, I think it's very an interesting tool. So now regarding gaze study, the comparison of gaze behavior in real and virtual environment. This last year, there has been some study who compare the gaze behavior in these two environments. They show that the gaze behavior was qualitatively similar, but there is more head rotation in VR. And more important, for these two studies, people perform a static task. So they were seated in the environment and they have to observe the scene as either light or a person moving object. And in our situation, we want to study how VR impacts gaze behavior while working in a dynamic environment. So to do that, we designed a task where a participant has to walk toward target and avoid any collision with the other worker. And we only analyze the gaze behavior during the interaction. So for us, the interaction is when the other worker is not hiding anymore by the wall, and it finished when the two workers are the closest distance to each other. We had 70 participants performing in all 130 trials. So we study 5 conditions, and for each condition, I will show you what kind of display, locomotion interface, and eye tracker we used. The first one was the real environment. And you can see the two occur. It will be our baseline for our next result. Then we look at virtual condition, and just to be sure, in virtual environment, the other worker was a virtual character. So the second one is where a participant were HMD, and he was able physically to move in the virtual environment. Then we had the same situation with a HMD, but he used a gamepad to move in the virtual environment. We also had a situation in a cave using a joystick to move. And finally, a screen with a joystick, and people have had their head on a chin rest. So as you can see, we have two kinds of locomotion interface, either physically work in the environment or using gamepad or joystick. We also have 4 different virtual reality setups with different field of view and peripheral vision. And now, regarding our hypothesis, the task will be the same in the 5 conditions. So we expect that people will look at of the element of the scene in the same proportion. However, as you have seen, we have different field of view, peripheral vision for the display. So we suppose that there will be differences in gaze movement between VR and real environment. And to look at this, we look at the gaze allocation, which is the proportion of time we pass on each element on the scene, the gaze movement, and I represent these 2 variables. We also look at trajectories and gaze fixation, and they are in the paper. So regarding the recorded data, here you can see during all the experiments we are able to record the trajectory, the gaze behavior, and also what the participant look at, either the other worker, the target, and the environment. Now, the same record data for a virtual situation. I will now present you results about the gaze allocation on each element, so either worker, target, and environment. And what you can see is that there is some statistical difference within the virtual reality setups. But there is no difference between real and virtual condition, which validates our first hypothesis is that we look at, either in virtual and real, we look at the same elements in the same proportion. Now I will be more on the gaze movement, and first we decompose this gaze movement. So the gaze movement is, in fact, the angle between the heading and the head, and also the angle between the gaze and the head. The second angle is, in fact, just the eye movement. And we look at this. But we also want to look at how participants look at on the element. So we want to study the angle between the target and the gaze, and the angle between the worker and the gaze. So for all this angle, we look at their evolution over the interaction, but over the normalized time interaction. So as I said earlier, the start interaction is when the other worker is not hid anymore by the wall. The end is when they are the closest to each other. And for the real situation, which is our baseline, what we can see is that there is little rotation of the head during the interaction. Now, if you look at the rotation for the cave, HMD working, and HMD controller, we have more rotation, which is consistent with previous study. And as you can see, there is no plot for the screen. Participants had their head on the chin rest, so they couldn't move their head for this condition. Now, if we look at the angle between the head and the gaze, you can see that there is no statistical difference between the last 3 virtual conditions and the real condition. And if we plot for the screen, we see a large difference between the screen and all other conditions. It's because they couldn't move their head, so all the movement was done by the eye. Now we look at the angle between the gaze and the target. And first, what we can see for the real situation is that people start to looking away from the target. It's because the other worker is coming in their field of view. So they will maybe look at him. And after, they're looking towards the target. It's their goal, so they have to look towards this. If we plot the same for the cave, we see that the peak is higher than real, but it happened around the same time. Now, if we plot for the other 3 conditions, this peak is also higher than real, but it happens sooner. And we suppose it's because the cave offers a better peripheral view and field of view than the other 3. Now, the same for the angle between the gaze and the worker. We see that it's progressively looking toward. We don't have this peak, but we have this peak for the cave, and we also have this peak for the other 3 and sooner. Again, we think it's because of the peripheral vision and the field of view. So if we sum up all this gaze movement and angle, we can see that there is lots of difference between real and virtual condition. And this is why we can validate our second hypothesis that, of the differences. And now I will come up with some recommendation for locomotion and gaze study. So for the cave, we had some eye tracking issue. It's because when you are in a cave, it's a very dark room, and our eye tracker needs some light to be able to track the gaze. So because of this, we have to remove the data from 3 participants. We don't recommend the screen because it prevents head movement. It's not as immersive as the other condition. So we think that HMD setup provides the best compromise to do study about locomotion and gaze. Now, regarding conclusion, in this paper, we propose a methodology to evaluate gaze activity. Our research shows that VR has potential for qualitative analysis of gaze behavior. When I say qualitative analysis, it's because, as I explained earlier, during the whole interaction, we look at the element in the same proportion. It's the gaze movement which change. So that's why it has potential for qualitative analysis. And now, in our future work, what we want to do is, as in the first slide, we want to study more complex situations about gaze in a crowd with lots of interaction with walkers. We also want to study new heuristics to describe gaze behavior. We just look at angle and gaze allocation, but there's lots of heuristics. And finally, the best thing would be to have HMD with larger field of view. I think that's lots of people want to have. So thank you for your attention, and do you have some questions?
Plenty of time for questions.
Hi, great talk. My name is Haley Adams from Vanderbilt University. I'm curious, how did you control for speed in the real world condition?
In the real condition, first we had the participant do a little walking to calculate his average speed. And so we calculate this comfort speed to have the same situation in the virtual condition. I think if it's answered.
I have a question. So we heard about the state of the tech. How is state of the tech in terms of eye tracking? Did you find the eye trackers were very reliable for what you were trying to do?
So eye tracker. As you know, eye tracking is something difficult, very noisy data, and sometimes it can be hard. So we use the FOV, and the FOV, I think it's very dependable eye tracker. It's well designed, and as I said, for the cave, we don't find a good eye tracker because we need this light for now for tracking the eye. And for this one, it was very hard. So that's why we recommend the HMD and maybe the FOV or other one, because I think in the FOV, you control the light. You have the light of the screen, and it's all embedded, and it's very more easy, I think, to track it in HMD than in other situation.
All right, let's thank the speaker.
Thank you.